Hello, Professor. Is it audible? Hello, Professor.
Yes.
Oh, okay.
Hello.
Yes, sir. Welcome, sir. Welcome. Sir.
Hi.
Yeah, thank you, sir. Thank you so much.
I'm ready.
Yes, sir.
Don't
Yes, sir.
worry.
Okay. Thank you.
Whenever you are ready, I'm ready.
Yes, sir. Thank you, sir. Thank you so much.
Thank you.
Sir, Kamraj sir, Professor sir, Dean sir. Dean sir. Sir, are you there?
Me?
No, sir, no, sir.
Oh, sorry, I thought so.
Yes, sir. Yes. Balaji?
Hi, sir.
Very sorry, sir, not joined right now.
I'll call him, sir.
Okay.
It's 2 minutes, sir. He's coming, sir.
Okay, okay. Professor, good afternoon, sir. Sir, mic not working.
Yeah, very good afternoon. Welcome, Professor Ismail, sir.
Thank you.
So we are very happy to see you in our conference. Thank you very much for joining us. Balamuldan, are you going to introduce or?
Yes, sir. Yes, sir.
Yeah. Perfect.
Yeah. Thank you. Thank you. Yeah, I welcome all the delegates to the afternoon session of the International Conference on Computer Science and Mathematics, organized by New Research and Innovation Society. I welcome our guest of the day and the keynote speaker, Professor Ismail. He is from Turkey, and I now invite Professor Balamuralidharan to introduce the professor,
Okay, sir.
the keynote speaker. Yes,
Okay.
sir.
Okay. Actually, the SAR resume, I received a SAR resume. Actually, it has 151 pages. In my life, I don't see such types of very big resume biodata.
Okay.
It's a very big. Very shortly, I tell you something. Okay.
Okay.
Okay, sir. He's a professor Ismail. Sir from the Faculty of Arts and Science, Department of Mathematics, Turkey. The total number of pages in his resume is 151. Actually, here he published more lot of publications. For example, Google Scholar ID, Google Scholar publication 352, citation 3158, H index 27, Scopus 180 papers published, citation 1488, H index 20. Mentally also publication 146, citation 936, H index 15. In overall publication in all the databases and other databases, researcher ID is a Web of Science. Web of Science publications 180, citation 1307, H index 18. Here, Char has given lot of information. Very shortly, I have to give some information only. Sir, title of his PhD thesis completed 1994. Normal subgroup of Haki groups. Then he wrote 90 books, over 370 scientific research papers, which are in SCI indexed and Web of Science database, 370. Then another, he organized 8 large-scale international congresses, scientific committee of 60 international conferences. He completed 17 MSc student and 22 PhD student. 22 PhD student is a very big achievement. Then sir got lot of medal and a lot of Q1 and Q2 journal. Lot of things are given. Then 34 international scientific journals. It's an editorial board. He has right now, he has been continuing editorial positions in 34 international scientific journals and 200 journals and peer-reviewed journal 200 journals, and the member of 7 national and international societies. Lot of things are there. Due to less time, sir, please take over this session, sir. It's a very wonderful CV, sir. I don't.
Sir, we are very much honored to have you here, sir.
Yes,
Thank you very
Thanks,
much. It's my honor.
Thank you, sir.
Thank you very much. All my friends know that India is my second country, so I feel like it, and I enjoy every time when I visit, especially physically, but this time only online is possible. But I'm sure one day we shall meet physically as well with my friends
Sir,
in
sure.
there, Chennai. So I would like to thank the organizing committee, especially to my friend Govindan Vedyapan, for inviting me to this conference, International Conference on Computer Science and Mathematics, COMAT 2023. It's organized by New Research and Innovation Society in Chennai. I'm proud to be a part of such a nice and important congress, first of all. My talk will be a little bit different maybe than the others because I checked the titles and they are all applications of mathematics. Mine is also application, but theoretical part is there. I want to give the young friends especially how we think in mathematics when we do something, when we got some clue for some theory, how we proceed. So let me share my screen. I think it's okay. Realization numbering graphs. So let me start by the fundamentals first. What we need, I shall give you in brief, in a very basic level, not too details. We have a set of integers. As you see, it starts from 1, so positive integers. These numbers are multiplicities. So that means in D of G, it's a degree sequence, it will be called. So there are A1 times 1s. For example, in this figure, in this graph, there is one here, there is another one here. So there are 2 1s. For example, 4s, let's see degree 4 vertices. This is of degree 4 because it has 4 connections, you see, with other vertices. And this also has degree 4. So there are 2 vertices of degree 4, but there is only one vertex of degree 2, for example. This is the one, okay? So now, my friends, this is a graph. There are, of course, many types of graphs according to your needs: directed graphs, oriented graphs, hypergraphs, simple graphs, non-simple graphs, planar graphs. You can classify graphs in many ways. But today, we shall not be dealing with these details. We shall be dealing with just numbers and graphs, okay? So for such a figure, for such a graph given to you, it's not too difficult, as you can see, to write this set, okay? 1, 1, 2, 3, 3, 4, 4. You just write them either as I read them or with multiplicities like this, doesn't matter, okay? So D is something like this. Out of a graph, we can write such a set. On contrary, my friends, given a set like this, the problem is, can we obtain any graphs, at least one? If there is one, how many? If there is a question answer to this, then how? So lots of questions follow. So let's go. For example, for this set, 1, 3 times 2, and another 3, okay? So 5 vertices with these given degrees. You see, this graph on the left has only one, only 1, 3, and 3 vertices of degree 2. Same here on the right-hand side. So what it says to us, if you are given such a set, 1, 2, 2, 2, 3, okay? For these positive integers, we have at least 2 realizations. We call these realizations of the set. So if such a given set, if you can draw a graph, then this set is realizable, and these graphs are realizations. Okay, it can be real. That's the meaning, actually. So the problem is, out of such a set, how we can get these graphs? How many? In which way? Okay, what algorithm? Many problems you can ask. So this side is more difficult given the integers to get. So, my friends, definition of omega invariant I should give first, because my talk is related to omega invariant, which is a new invariant. In mathematics, invariants are very important. For example, there is the most famous one, Euler invariant, since 17th century, maybe, or 18th century beginning. So sometimes if you have an invariant, it goes on forever until the time goes, wherever it goes. We don't know, of course. So what is the idea behind defining such an invariant, another new invariant? Is it important? What it means? Okay. So in a tree, this is literature, from the literature. In a tree, the number of leaves that is pendant. Another term, degree 1 vertices. You see there are lots of them in this picture. Is equal to, A1 was, if you remember degree sequence, A1 was the multiplicity of 1. So A1 is equal to the number of trees in the graph, in your tree, twice the number of 4s, vertices of degree 4, 3 times A5, 4 times A6, delta minus 2 times A delta. So this is well known in some books of graph theory about the number of leaves of a tree. This number 2 does not change for any tree. This relation is satisfied. You can check from this example. You can put all the numbers and you can check that A1 is indeed 2 times 3 plus 2, 8. Indeed, there are 1, 2, 3, 4, 5, 6, 7, 8 vertices of degree 1. In a tree, this is satisfied. So what about non-trees? If you have a cyclic graph, which has at least one cycle, closed region, what this relation becomes? Does it change or is it still valid? So, my friends, if you reorganize this formula, if you take 2 to the left, and if you take A1 to the right as minus A1, okay? So you get this formula, you see A3, you remember this part, 2 times A4, 3 times A5, 4 times A6, 5 times A7, like this, up to the largest vertex degree, delta minus 2 times the multiplicity of delta, A delta, and minus A1. Maybe if you are very careful and if you are concentrated, you have realized that there is some term missing. Which one is it? It is, yes, A2. A2 is missing because A2 means 2 minus 2 is 0. So the coefficient of A2, which normally appears here, but with coefficient 0. So we don't write it here. For A1, we put 1 here, 1 minus 2 minus 1, minus 1 times A1. But if you put 4, for example, this one, A4, the coefficient 5 minus 2. So we start with A3 always, okay? This is the method, practical method. There are many very practical geometrical methods actually, but today I shall try to give some of them. A3, 2A4, 3A5, like this, we go to the end, and at the end we put 1 times A1 or just A1, okay? This is the sum, and we called it omega invariant. Omega invariant, okay, it's a formula. In mathematics, everybody can write, for example, if you change this A3 to 5 times A3, this is another formula. You can call it omega dashed, for example. It's another formula. But to define such a formula is very easy. Every day, thousands of people define new formulae, okay? The thing is, are they useful or do they have some mathematical nice identities, properties, corollaries, lemmas, okay? That's the important thing. If it has no meaning mathematically, no picture, no beautifulness, okay? No aesthetics, okay? And also no application, this formula must die, okay? It will not go forever. But if it has some applications or if it has some nice mathematical properties, then this formula will be used many other times and your papers will get attention will get cited. So this is omega invariant. What is the meaning? To understand the meaning, I'll give you an example. This is a graph, non-simple graph, because it has a loop. This is the degree sequence of this graph. There are two vertices of degree 1, you see. There is one vertex of degree 7, this one, next to the loop, incident to the loop, okay? This vertex, for example, is of degree 3. This vertex is of degree 2. This is of degree 4. So if you list all these, you get this set. Then omega, how we calculate, you must remember, we start with A3. A3 is the multiplicity of 3, which is 2. So you can write this 3 minus 2 times 2. 4 minus 2 times 1. 5 minus 2 times 1. 7 minus 2 times 1. So we reached to the end. Now, finally, you remember minus A1, minus 2 must be there. So we get 10. What is 10? Just try to comment. What is 10 for this graph? Is it the number of vertices? No, it is less. Is it the number of edges? No, it's not. It's more. Is it the number of faces? 1, 2, 3, 4, 5, 6, like this? No, it does not. It's not. So what is it? This number 10, if we are going to do some definition as omega invariant, must have some importance, okay? We feel it, but we have to show it, and we have to prove it. First, in mathematics, always we are suspicious of some results. Looking at some pattern, looking at some numbers, looking at some results, existing results, and we conclude, we estimate some results. This should be like this, we say first. But if we believe it, infinitely many, doesn't matter. If we believe it from our heart, it's not enough for it to be real, to be a theorem, okay? We have to prove it always. To give examples 1 million times is not enough for a mathematician, because there are theorems, I know one, it is true for a natural number up to 1 million something. There is only one problem with 1,032,000, something like this. Afterwards, it is always true. So, my friends, only one example after 1 million try is demolishing this theorem. It's not a theorem. You have to put this condition, okay? If n is different than 1 million something, then this is true, we should say. One counterexample damages everything, okay? So now we shall give the properties of omega. For any graph G, omega invariant is equal to 2 times m minus n. 2 times m minus n. M is the number of edges, n is the number of vertices. So, my friends, these are counting numbers naturally. Twice the counting number is an even. Got first is omega invariant is always an even number. M is the number of edges, n is the number of a graph. You can count m and n, and you can calculate omega easily without looking at the. We have only vertex degrees. So out of these vertex degrees, we have to form a graph, or many graphs we have to form. So omega is an even number. So that means if someone is given you some set of integers like above, and if you calculate omega as an odd number, then this set will not be realizable. You will not get any graph out of it. So if omega is odd, this is going to the rubbish bin, okay? very strong condition, the necessary and sufficient condition for a simple and connected planar graph to be a tree is omega equals to -2. This is very particular case. Omega is an even number. It could be -6, -4, -2, 0, 2, 4, 6, 8, 10, whatever. Many, infinitely many integers, of course, even integers. It could be. For simple connected graphs, if you want a tree, then omega is -2. If omega is -2 and if you want a connected realization, then again, it must be a tree, okay? -2 is reserved for graphs. We shall remember this. This is very important. Such a set is given, such a set D is given, and it is realizable. That means there is at least one graph out of it. And C components, there are C components. For example, if you want a connected one, C is 1. If you wanted two pieces, like some networks, okay, there's a group of people or items here, there's another group here. Between them, there are connections maybe or not. So this is increasing the number of components. So this is the number of faces formula, which is very important. I shall remind you this. The number of faces will be a half omega plus the number of components. For example, if you want a connected realization, C will be 1. Omega, let's say 10. 10 divided by 2 is 5, plus 1, 6. So if you remember my example here, omega was 10. So 10 divided by 2 is 5. And as this is connected, we add only 1, 6. So this is the number of faces. So this is one face. This is 2. This is 3. Here, if you pull this string to the left, there will be an upper triangle, there will be a lower triangle, and there will be a region here, okay? Like a crescent. Related to omega. The number of faces is related to omega. So this formula is important. I shall use it later. This is a lower bound for the number of components in any graph. It is bounded by below by minus omega a half, okay? Minus omega divided by 2, which is equal to n minus m. So in any graph realization, the number of components will be at least the number of vertices minus the number of edges. If you know these numbers, then you know that it can be connected or it cannot be connected, because if C is at least 2, then it means C cannot be 1. C cannot be 1 means it cannot be a connected graph. This is important, but only one slide. But behind this slide, there's a theory, of course. We grouped all the graphs according to realizations and omega invariant. Omega is -2 is one class. Omega is -2. If you remember, 3s usually. Omega is greater than or equal to 0. Omega is greater than or equal to 0. And omega is less than or equal to -4. You remember, only even values it can take. -2, 0, 2, 4, 5, 4, 6, 10, 8, this part. And -4, -6, -8, -10. These three groups will have different properties, different theorems, different algorithms for everything. So in terms of omega, we have three groups. Now, my friends, time is running away, running out already. Some 20 some minutes passed. So let me continue with proposing some problems. The first problem is about such a set. This set is given. Is it realizable? What is it asking? Can you find at least one graph with vertex degrees given in this set. There must be one vertex of degree 7. There must be one vertex of degree 5. There must be 3 vertices of degree 1, pendant vertices, you see, degree 1. So this is realizable or not? In that point, I should say that there are many tests, actually, algorithms. The most famous one is Havel-Hakimi process. Havel is a Czech mathematician and Hakimi is Iranian mathematician. In 1955 and 1962, they independently obtained the same results. Yeah, there was no internet, so they was not aware of each other's result. Havel-Hakimi process is an algorithm which works very nicely to decide whether you can get a graph out of these numbers. But we give much more compact form with this problem by using omega invariant. What is the cyclomatic number? Cyclomatic number is the number R, the number of regions, independent cycles, okay, of any connected. C is 1, okay? We shall come back to the next problem, but first we should go through this. The problem asks you, this set is realizable or not? Now we know that if omega is even, omega is 14. Let's do it once more for those who didn't get how we calculate. 3 times, we start with 3 always. 3 times 3 minus 2, which is 3 times 1. We get 3, okay? 3 times 4 minus 2, which is 6. We got 9. 1 times 5 minus 2 times 5, we got 17, and minus 3, 14. You see 14, it's correct, okay? We checked it. So it is even, that means, oh good, my God, we can find at least one graph, in fact, thousands maybe, okay? In at least one graph with these vertex degrees. So this is realizable, this set is realizable. What about the cyclomatic number, the number of faces? It was, if you remember, R equals to omega half plus C. C is 1 because it asks you connected realization. So this is 1, you see. Omega is 14, so we got 8. So that means any connected realization of this set, there might be thousands of realizations because lots of vertices are there, okay, must have 8 faces. If you draw already 5 faces, you should add 3 more faces, okay? So if you know the number of faces, drawing some picture is important. It's very easy, okay? Because, for example, if you reach to the 8th face, you already got 8 faces, then you don't add any loops or chords which causes another face, okay? So this is important. Second problem, it asks you, what is the minimum and maximum number of components? Now, my friends, to see the problem, you are given a set, 4 3s, 2 4s, and 2 5s. So that means there are 8 vertices, 4 plus 2 plus 2, with these vertex degrees, okay? This is an 8 vertex graph. But ways, okay? Many ways, many graphs around you are there. What is the minimum number of components? For example, can you draw at least one connected realization? Or if minimum number is 3, for example, for the number of components, what you can say, so we cannot have any connected. component connected realization, or even we cannot have a graph with two components because minimum number is 3. So you must have one piece here, another piece here, 3 pieces. And what is the maximum number? So if you have maximum number of components, each component must be very small. If possible, only one vertex you must use. One vertex forms a graph by itself if it has even degree. For any degree, odd degree vertex, we cannot form a graph because handshaking lemma does not allow you. The sum of vertex degrees must be even. So, by corollary, we gave before, the lower bound, you remember, was minus omega divided by 2, or n minus m, if you remember. Minus omega divided by 2 means minus 6. So, my friends, C is the number of something, counting number. If you know some counting number is greater than good, of course not. So we take C as 1 because it's a counting number. It starts with 0, 1, 2, 3, okay? If you count, if there is some example, it must be at least 1. So that means if C can be 1, the most lowest possible case, then at least one graph can be connected. But probably this is the minimum one. There could be larger values of C, so it could be disconnected as well. So my friends, let's go faster. This is the minimum number for C, minimum lower bound. What about the upper bound? It is C max, maximum number of components, which is equal to AI, the sum of AIs over even degree vertices, okay? Even vertex degrees, let me say. And a half times the same sum, but this time where we take the i's as odd ones. For example, this one will form A2 plus A4 plus A6 plus A8. This goes like this. And this goes like this. 1 plus 2 brackets, A1, A3, A5, A7, A9, whatever it goes, okay? So this is the number of maximum number of components amongst all realizations. So if you calculate these two numbers, C minimum and C maximum, you know that the realizations of this set will have at least, say, 3 components and maximum 7 components. So you don't look for graphs which are connected or graphs which have 8 components. 7. This is very important, especially in computation. When you use infinitely many numbers, then you have to put such conditions, some limits, upper bounds, lower bounds. So by this theorem, C max will be 5, and this is 5 component realization. You see, this is a vertex of degree 4. This is a vertex of degree 4 again here. So only with 4 we can form a graph. You see, this vertex has degree 4. 2 is going up, 2 is going down. It's not a simple one. It has loops, but doesn't matter. There's no condition. But this, for example, vertex 3, vertex degree 3, vertex degree 3, you take 2 of them because the sum of vertex degrees in any graph and in any component must be even. So if you take only one odd number, it's no good. You must be having another one to accompany it, okay, to form the sum equals to an even number. So this is maximum of this set could have either one component, which means connected, or 2, 3, 4, and 5 components maximum. That's easy. How can we decide whether a realization of a given degree sequence is connected? This is a big problem, my friends. Given numbers, just imagine one moment. 1, 1, 1, 2, 2, 2, 3, 3, 5, 7, 8. Okay? It is realizable, let's say. I say it randomly. You can choose any set. There are many graphs, you know that, out of this set, but connected or not. So what can we say? For this set, I gave you an example. 1 6 times, 4 twice. You see 4 twice, 4 twice, and around them 6 vertices of degree 1. 6 vertices of degree 1. Okay? So for this set, my friends, we can have sometimes connected realization, sometimes disconnected. So what can we say? So this is the main result. If omega is less than or equal to -4, all realizations will be disconnected. I would like to say many things about this, but this is the point you have to remember. Omega is less than or equal to -4 means you cannot do anything to get a connected realization. Always you have disconnected realizations, okay? And if omega is at least -2, then potentially connected realization, at least one potential realization. This is the meaning, potentially connected, okay? Okay, if omega is, for example, -4, -6, -8, then no connected case. It's not possible. There are examples here. I will skip this. How we can find connected realizations? We gave, you remember, 3 cases, 3 groups. Omega equals to -2, the right-hand side, the left-hand side. So in each case, in each group, in each family of graphs, we have algorithms. For example, for this one, omega is 0. For this example, you can calculate omega. Omega is 0, so that means D is realizable because it's even, and potentially connected because it's at least -2, just previous slide. To find connected realizations, we first draw 2 plus 3 plus 1 plus 2. What are these numbers? 2 plus 3. 2 is here, 3. We get 8. So we got octagon. Maximum length of the cycle in any realization could be 8. But it could be less because we gave a method of carrying vertices without damaging the degree set, okay? This is, for example, an octagonal face with some spices around it, spikes, okay? So this is a 7 gun with the same vertex degree. This is hexagon. This is a pentagon, okay? This is 4. This is triangular case. This is 2. This is 1. These 2 are rather different, rather unusual, because many people do not take this as a cycle, but this is 1 cycle, this is 2 cycle, because this is, if this is 7, this is 6, this is 5, this is 4, this is 3, in the same meaning, this is 2 and this is 1 cycle, okay? But in combinatorics, we take them, but in geometry, some people say that the cycle must have at least 3 edges, for example. So final problem I shall propose, how we can decide whether a given degree sequence is potentially connected. You remember potentially connected? You are given the integers, you look for at least one connected realization, okay? Can you say without drawing the graphs? Because you draw one graph, it may not be connected. Another one, you try many times, you cannot get some connected ones. It's possible. It's of vertices. So there is a theorem since 1964 by Edmonds. Edmonds says that this degree sequence is potentially connected if this condition is satisfied. Okay, you can control, you can check this condition. But omega invariant rephrase this theorem just like this. This is a degree sequence. This is potentially connected if and only if omega is at least -2. Omega is at least -2 means there is at least one connected graph. The proof is very easy. This is just to compare two methods. This is Edmonds' theorem. The result is it's potentially connected. This is omega invariant, just one line. You calculate 6. 6 is at least -2. So that means we have the result. Sometimes, my friends, to finish, omega invariant gives you new replies, new answers for open problems or for some new problems. Sometimes it rephrases in a compact form the existing theorems, and it makes the way to calculate shorter. This is a good, of course, opportunity. And one final combinatorial problem I shall propose. Maybe some young friends may think about it. For a given degree sequence, what is the number of realizations of the very big problem? But it is a sub-problem of this problem. What is the number of graphs having n vertices? We don't know this. We know it up to 52, I think, something like this. In the web, you can search for it. There is list of numbers of graphs up to billions, of course, with up to 52 vertices. If someone asks you how many graphs are there having 40 vertices, it is there in the computer. It's in the websites. But after 52, we don't know it yet. It's too big to calculate. And there is no formula for the existing formulas, okay? So it is a big problem. This is sub-problem. With some vertex degrees, some degree set, okay? So what we have done, we gave an algorithm I will not give today to calculate step by step some numbers, and up to some point, after some point, you calculate the sum of the numbers you obtained at each step. But the most problematic case here is canceling the same graphs from the list, because sometimes in different routes you get the same realizations without knowing them, because sometimes two graphs might be isomorphic, but they might look very different, like two views of K4, okay, or K33. So we have tried some algorithms, and some steps are already solved. Some cancellation are done, okay? And we got some formulae like this in combinatorial terms, in terms of permutations and combinations. And soon, I hope, we shall be finished with this problem. There are many, many, many papers already on omega invariant. If you think somehow omega invariant might be useful for your talk, your studies, then you may always contact me. This is the main paper, a new graph invariant in 2018 about omega invariant. The second one is extremal problems on components and loops. It was next year. And afterward, there has been about 60, 70 papers, some theses, okay? So it's very popular at the moment. This is omega and cyclicness, for example. This is Edmonds' theorem I gave you. This is Hakimi and Havel about realizations. Another one has been published recently. This is connectedness criteria by omega invariant. This is again nullities, matching number, omega invariant of some products of graphs, okay? Independence number by omega invariant. Omega invariant and cyclicness, maybe I mentioned already. Line graphs, unicyclic graphs, omega invariant. You can connect many things to omega invariant, especially if you work with topological graph indices. You can calculate many problems by omega invariant. So you see there are lots of applications of omega invariant in mathematics. Of course, chemistry has a lot of applications in molecular graph theory, molecular chemistry. The graphs are used there. In networks, graphs are used today. In brain studies, neuroscience, this kind of areas of medical studies, they use graph theory always. So in social science problems, people always use graphs very easily, because graph means there are items, people, neurons, cells, galaxies, doesn't matter, which have relations between them somehow, okay? So everything in real life can be modeled by a graph, and if you know mathematical method on these graphs, then you get some numbers, and you should comment on these numbers. Like this omega invariant, we got 10. What is 10? We wondered, okay? Afterwards, we see that lots of properties of it there, okay? So thank you very much for listening, my friends. I think I'm already over the time. Thank you for listening. If any questions you have, either you can ask now or you can contact me by email always.
Thank you very much, Professor. Thank you very much. Very nice presentation.
Thank you, my friend.
Thank you, sir.
Thank you.
Any questions from audience? You can raise your hand if you want to ask Professor any question or clarification. You can send message or raise question. Or you can later also send email to Professor. We have a Professor email we will share in the proceedings. You can always ask him. He will be there to help you. So, respected Professor, we are very honored by your presence in this international conference, for taking time and giving a wonderful talk to all our delegates in this afternoon of India. Thank you very much. And definitely we will meet when you visit India. If possible, we will also come to Turkey. Thank you, Professor. Thank you very much.
Why not?
Thanks a lot. Yeah, Balamuralidharan.
Yes, sir. Sir, thank you, sir. Thank you so much, sir. It's a very nice presentation. Very nice presentation.
Thank you.
You have given a lot of information. Sir, track 1 keep in the same.
Yes, sir.
Okay, track 2.
Delegates for track 2 shall leave and join track 2 for your oral presentation, and others be in this track itself, track 1 for oral presentation.
Sir, shall I leave, sir?
One second, sir. Sir, what about Kumar Nath and Balamurugan are there, sir, in the link?